Hi guys, welcome back to Data Every Day. Today we're looking at a data set of mental health in the tech industry. And basically it's a survey from different subjects. And we're going to try to predict whether the certain subject has sought treatment for a mental health condition. And so let's go into the notebook. And we're going to use a TensorFlow neural network to try to make some predictions. So let's import pandas and numpy to get started, just to work with the data. Matplotlib.pyplot for visualization and graphing. And then the standard scalar and train test split function from sklearn for preprocessing. And like I said, TensorFlow for the model. Alright, so I'm going to load in the data using pandas.readcsv. And we can get the CSV file right over here. I'm going to copy the file path, paste it in, take a look. We have 27 columns, which goes over the limit of what pandas will show at once. So we have this ... I want to see all the columns at once, so I'm going to go into the console and type pandas.setOption max columns. Whoops, none. And now if I run it, I can see all 27 columns. I have a scroll wheel at the bottom. So as you can see, there is very little numeric data in this dataset. It's almost all encoded as text values. So we're going to have to do extensive coding to try to get it, encoding to try to get it into a machine-readable format. So let's just start cleaning it. First thing we're going to do is get a nice quick clean. We're going to get a sense of how many missing values there are in this. We can see there are at least a few. We have true wherever there's a missing value and false otherwise. That's what this isNA function does. We sum over the rows. We'll get the number of missing values in each column. And this is very useful. We can see exactly how many are in each column. And you can see that we have 1, 2, 3, and 4 columns with missing values, which makes our lives easy. If they were in all the columns, it would take a lot longer. But let's instead of summing, we can take the mean over the rows, which means add up all the trues and then divide by the total number in each column to get the percentage missing values in each column. So you can see 40% of the values are missing in state, 86% are missing in comments, and that immediately is a red flag. This is too high. Too many missing values. Far too many. So we have to drop this column. It's not going to it would be counterproductive to keep this column. Now maybe if we were really trying to squeeze out every bit of information, we could try to, I think the comments are just like extra, it's like text that people have entered. Maybe we could parse through that and get some sort of like word embedding, but we're just going to drop it for our purposes. So it's just, it's too much for too little. So we're dropping comments from axis 1. And let's just refresh this. The 40% would be generally that'd be a very high number, but because the state, if you look at the data set, state is only applicable if the country is United States. So what we'll do is we'll one-hot encode the state. Here, let me show you what I mean. We can use pandas.getDummies and pass in data substate. And this will give each state in a new column, and we'll have a 1 in a given row, all zeros and a single 1 for the given state of that example. So example 0 is Illinois, so we have IL has 1, and all the rest are 0. But for the ones that are missing, is a very simple solution to this. You can see example 2 is a missing value there. Example 2 is just simply all zeros. So this encoding effectively deals with the missing values. We don't have to worry about filling them in or anything. If we just one-hot encode the state column, we'll have 1s when there is a state and all zeros when there isn't. So I don't have to worry about that 40%. Let's look back at the sum. Because now there's no more shockingly high percentages. State we already figured out. Now we're just down to self-employed and work interfere. So if we look at this, self-employed, looks like a binary column. Let's take a look. So I'm going to get the unique values of self-employed, so .unique, and we can either have yes or no, and then there's the missing values. And for this, because there's such a few number, 18 only, I'm just going to fill all the missing values with the most common occurrence. So we can get that self-employed dot mode. The mode would be the most common occurrence, and it is no. So I'm just going to fill the missing values of self-employed with no. So dot fill na will fill all our missing values with a given value, and we want to fill with no. And that's going to be our new column. Okay, now if we refresh this, you can see our self-employed missing values have gone away, and we're left with this final column, work interfere. Work interfere looks to me to be some sort of an ordinal feature. It has never, rarely, sometimes, often, maybe a few more. Let's take a look. So I'm going to work interfere. I'm going to get the unique values for this one. See what kind of data is in here. So we have, yeah, it looks like a pretty standard ordinal feature. There's a obvious ordering between the values, which means we're going to have to fill the values if we want to keep this column. So the missing values in an ordinal feature will not do. We can't just one-hot encode it or something. Although we could one-hot encode this. I want to encode it as an ordinal feature. So let's fill it with the mode, the same way we did here. So I'll just grab this and get the mode of the column, and it's sometimes. So we'll just do what we did up here, except this is now work interfere. And we're filling with sometimes now. Okay, now let's take one more look at this. You can see our only missing values are in state, and like I said, those will be taken care of with the one-hot encoding. So we're done cleaning the data, just a quick clean. Now we're going to move on to some feature engineering. So feature engineering involves taking data, taking columns, and creating new features out of them. So specifically, I want to feature engineer some date and time features out of the timestamp column. Right now the timestamp column is not of much use to us. What we could do with it now is ordinal encode it by sorting it in terms of recency. And the least recent, the farthest into the past would be the lowest value. The most recent would be the highest value. But we lose a lot of information doing that. For example, the month is extremely valuable in understanding time of year. And the cyclical information is sort of lost if we just encode it as an ordinal feature. So let's create some new values, some new columns out of the timestamp column. So we have this timestamp column, and I want to apply some functions to it. So we can use apply to apply a lambda function or any other function element-wise to each entry in the column. So it takes in some x, so x will be a single entry. It'll be one of these. And how do we want to process x so that we can get just the year? Well, it would be x from 0 to 4, just the first 4 characters of the string. And so if we look at this, this will just return the years for us. And when we're done with that, we can turn it into a NumPy integer. Now this is of type integer. And we can make a new column and call it year. Now, if we were to refresh the data, you can see at the end we should have a year column, that these are integers taken from the timestamp column. So let's go ahead and do that once for year, once for month, once for day. And it's up to you if you want to include the time values. I think hour might be useful. But just so we don't miss out on any data, any information here, I'm just going to do all of them. This is up to you though, what you think is useful, and you can experiment to see what actually is most effective, but I'm going to do hour, minute, second as well, just so you can see how to do it. So for month, we grab these two, which will be indexed from 5 to 7. For day, we'll grab these ones, which will be from 8 to 10. Then for time, well, let's look, it's easier to look here. The hour will be given by these two, which will be 11 to 13. Notice we're skipping one that accounts for these separators each time. Then we need the minute, which is given by 14. Sorry, wait, is this correct? I want to make sure I'm doing it right. Yeah, it's 14 to 16. And then the last one, which will be the second, these two at the end, will be 17 to 19. Alright, and when we're done with all that, how about we drop the timestamp column? So it's actually no longer of any use to us. So we can say data equals data.drop timestamp axis 1. Okay, let's run it through once more and then take a look. We now have the timestamp column is gone, but we have these year, month, day, hour, minute, second features, and they're all integers. So this is a sort of encoding it as we process it. I mean, it was already numerical data, so. Okay, but now let's start encoding. Let's encode the features. So when I start encoding features, the first thing I like to do is get a sense of what kind of data is in each categorical column, and also what kind of how many unique values are in each categorical column. So let's create a dictionary that's going to map a column name, to the length of unique values in the column. And that's going to be for every column in not data.columns directly, because that would give us the numerical columns as well. But if we do data.select dtypes, and then specify a type, which will be object, which will correspond to string, and then get the columns of that, if we just look at this, for example, if we just run that, we can see this is a list of all of the object columns. They're all of type object. So if we're getting the dictionary now that maps a column name to the length of unique values in the column for every object column, we get this, which is a very nice way of visualizing how many different values we have in each column, because this will help us understand how to encode each feature. And then additionally, I'd like to also display not just the length, but a list of each unique set of unique values for each column. So now I can actually go through, and it might be easier to visualize if we don't make it a list. No, that's not better. Let's keep it as a list. It just stacks this way for sort of a long format. Something we notice is that the gender column has some non-binary entries, right? So we can't just make this a male or female column. We're going to create 3 values that will be male, female, or other. And you note that people entered it as they wished, so that we have M, capital M, lowercase m, capital male, lowercase male, and so on. So what we're going to do is, this may not be the best way to encode it. There's certainly other ways to do this, but I'm going to just take the gender column and deal with this first, because it's sort of a unique occurrence. You see all the others, the users were given choices instead of entering their own values, so it's much more predictable. But for the gender column, what I'm going to do is apply a lambda function that takes in some x, which will be a given value in the gender column. Actually, I'm not going to apply a lambda function. I'm going to create my own function first. Let's call it encode gender. And it's going to take an x, which would be a given entry of the column. And what I'll do is if x, which is our gender, dot lower, which will set it to all lowercase, sub 0, which means the first letter, equals f, we're going to return 0. Elif x dot lower sub 0, equals m, return 1, and else return 2. So this way we have 3 values. Now this may not account for example, this person wrote guy, which I assume is male. I mean, it's not so straightforward, but it's not going to capture intricacies like that. However, this seems like a pretty good way to encode the column. So I'm going to do this encode gender, and now I'm going to apply encode gender to the gender column. You can see that will turn it into 1s, 0s, and 2s. We take the unique value. The unique values of here will have 0, 1, 2, and we can make that the new gender column. So we've dealt with gender. Okay. Now if we reload these, you can see we don't have gender at the top anymore. We now have to encode the rest, and the rest are, we know there's only missing values in the state column. So, and we already know that's being 1-hot encoded. So for the rest, we can assume that this number of values is actually saying how many real values there are in each one. So for country, okay, so let's do it this way. Let's create 3 lists. Binary features, ordinal features, and nominal features. And we're going to basically sort each column name into one of these 3 bins. So let's open them up, and we'll go one by one. So country has 48 unique values, and we know they're not in any order, so I'm putting country in nominal. Then we have state, which we know already is nominal. Then we have self-employed. This is binary since it has 2 values. Family history, also binary. Treatment, this is our target variable, so I'm going to store it separately. Target equals treatment. Work interfere, this is ordinal because there's a progression between them. Number of employees, also ordinal. You can see there's an ordering between them. Remote work, this is binary. Tech company, also binary. Benefits, nominal. There's 3 values, yes, no, or don't know. Care options, also nominal. So there's 3 values. Wellness program, this is nominal. Seek help, also nominal. And anonymity, also nominal. Just grab these. And then leave, this is nominal as well. We might consider making this ordinal, but because the don't know is in there, it'll make it difficult. Mental health consequence, this is nominal, so there's a maybe. You know, you might be able to encode the maybe as ordinal, as this, it would be like 0, 1, 2, but we'll just do it as nominal. Physical health consequence, also nominal. Co-workers, also nominal. We're almost done here. Supervisor, also nominal. Mental health interview, also nominal. Mental versus physical, also nominal. And finally, OBS consequence, that is binary. Okay, so now we have sorted out all of our different columns, and let's create some functions to encode them now. So I'm going to create 3 functions: binary encode, ordinal encode, and 1-hot encode. So each one is going to take a data frame and some columns. And then the binary encode is going to take a list of positive values. The ordinal code is going to take a list of orderings. And the 1-hot encode is going to take a list of prefixes. So now let's start coding. We're going to start off all 3 by creating a copy of the data frame. And then for each column And other value, for this it's positive value. For this it's ordering. And for this it's prefix in the zipped form of columns and the list. So here's positive values, here it's orderings, here it's prefixes. So for each one, we're going to, actually just dealing with these now, we're going to apply a lambda function. So actually it should be like this. df subcolumn equals df subcolumn dot apply lambda, and then for the binary encoding, we're going to well, each one takes in an x, right? For the binary encoding, x will become 1 if x equals positive value, and otherwise becomes 0. And here, x will become ordering.index of x. So this will take an ordering, which will be a list of the values in the column, and send it to a unique integer represented by the index in the list. This one is going to just set x to 1 if it's the positive value, and otherwise 0. And then at the end, we'll just return the data frame. Now for one-hot encoding, we're going to create some dummies. This will be just what I did earlier with the get dummies for the one-hot columns, and that'll be for df subcolumn, and we'll include a prefix, which will just give all of the one-hot columns a prefix. Then, whoops, no colon. Then we'll concatenate using pandas.concat the original data frame and the new dummies side by side on axis 1. When we're done, we're going to drop the original column from which we created the dummies. Return df. Okay, that's it. And now let's create some positive values for the binary features. So binary positive values equals, it's going to be yes, but we want a bunch of yeses for every feature in binary features, because all of the binary features had yes as the positive value. Now the ordinal orderings, this I'm just going to paste them in because I already have them written. I don't want to type them out again. This is just ranking for the work interfere and the number of employees each ordering. And then the prefixes I'm also going to paste in. They're just annoying. It's just the first 2 letters of each column with a few changes. And then we're going to, okay, let's do this. Alright, so let's encode the 3 different types. Data equals binary encode. I'm going to pass in data, and then the columns, which will just be given by binary features. And then we're going to specify some positive values, which will be the binary positive values. Okay, then we're going to do it for the ordinal columns. So ordinal encode, pass in data, pass in some columns, which will be the ordinal features, just these 2. And then the ordinal orderings, actually it's just called orderings, is going to be given by ordinal orderings. And then finally we'll do it for the one-hot features. So data columns equals nominal features. And then our prefixes will be given by nominal prefixes. Alright, I'm running that. Binary encode. Oh, let me just rerun the notebook. Positive values, unexpected keyword argument. So binary should take positive. I misspelled it. Positive and positive. Okay. There we go. Take a look at the data. You can see we now have. Oh, interesting. Look at this. It doesn't seem to have. Did we forget to put physical health interview in our nominal features? Looks like it. So let's look up here. Physical health interview came right after mental health interview. And I think I already had the prefix for it. Yeah, I did. PI for physical interview. So let's just redo this. I'll rerun the whole notebook. Take a look at data. We now have only one remaining column to work with. So what we can do is data.select dtypes object to get all the columns that have object data type. And you see there's only one left, which is treatment. And that's our label column, or our target column. So let's encode that now. Encoding labels. For this, we'll just apply binary encode to the label column. So data equals binary encode. Pass in data. Now I'll do it on one line because it's just one column. The columns is just going to be a single column, treatment. And the positive values is just going to be one positive value, which is yes. Alright, run that. Now if we look at the data types, we can see there are no more. So if we get .columns and take the length, we can print out remaining non-numeric columns. 0. So we are done encoding the data. Everything is in numeric form, and there are no more missing values. Right? We should also note that. Print remaining missing values. That will be given by data.isNA.sum. So I remember I summed over the rows to get the number of missing values in each column. And I can sum over the columns again to get the number of missing values in the entire data set, which is 0. So we have no more non-numeric columns and no more missing values. We're ready to split and scale the data. So splitting the data will involve taking our treatment column, which is what we're trying to predict, and splitting it away from the rest of the data. So let's call that y. Y will be just the treatment column, and I'll make a deep copy of it. And x will be everything except the treatment column. So I'm dropping it from axis 1 and making a copy of that. Then we can create a scalar, which will be a standard scalar from sklearn. This will give every column mean 0 and unit variance. So x equals scalar.fit transform x. And then we can split into a train and test set. So now we're splitting horizontally, splitting rows. So we'll use the train test split function for this. Train test split from sklearn. We can pass in x and y. So what we're trying the two different one's a data frame, one's a series, but we're trying to split them at the same place. So let's specify a train size of 70%, and that's going to generate 4 new data frames. Well, the y's will be series. X train, x test, y train, y test. And we can include a random state as well, just so that we can reproduce the results. Because this function also shuffles the data, which takes we don't have to do that ourselves if we use this function. Alright, so now we're ready to train. So we're going to use TensorFlow, and I'm going to start building a Keras model using tf.keras.input. This will be our input layer. The shape will be, well, if we look at the shape of x.shape, you can see we have 149 features. So we're going to feed in a single vector of length 149 for each example. So I could type 149 comma to give a vector of length 149, but I want this to adapt to x, so I'll do x.shape sub 1. Right, now we're going to have 2 hidden layers, fully connected layers. So tf.keras.layers.dense. And I found that we need a few more neurons than usual for this dataset. 1024 seemed to work well with a ReLU activation. Let me pass in the inputs. Alright, we have a second one. This is the same except we pass in x. And then we have our outputs. Nothing fancy. This will return 1 activation and a sigmoid activation function so that we get this one value will be a probability estimate, so between 0 and 1, of prediction for the positive class. So tf.keros.model, inputs, outputs. So essentially this model will output a prediction for a given example of length 149. It will give us a prediction of how likely the candidate is to have sought out mental health help. Alright, model.compile. I'll compile the model using an atom optimizer. For a loss function, we'll use binary cross entropy. And for metrics, we'll include accuracy. We can also do AUC. So another nice binary classification metric. Okay. In this case, we don't really need this because I believe actually we should check. So y is basically ones and zeros, and y train is really what we care about. It's ones and zeros. So if we take the mean of it, it'll sum up all the ones and divide by the length. So we'll get the percentage of ones in the data set, and this gives us a sense of the class distribution. I could even print it. Print class distribution, and I'll use formatted strings here. And I'll format. So this will be positive to negative. So the mean of y train will be the percent positive, and 1 minus the mean of y train will be the percent negative. So I want to multiply by 100 so we can get percentage values. So over here I'll multiply by 100 as well. And another one of these. Alright, so 49%, 49.7% positive, 50.3% negative. Very even split, almost perfectly 50-50. So this metric is not necessary. Accuracy gives us a good idea. However, this metric will tell us if one of our classes is performing worse than the others. But there's other ways to do that as well. I just thought it'd be nice to have both metrics here. Alright, batch size. Let's make it, I don't know, 64. Number of epochs. We can train for 50 epochs, and I'm going to use the reduced learning rate on plateau callback. So history equals model.fit. We're going to train the model and store its results in history. And then I'm going to pass in the training set, xtrain, ytrain. Give it a validation split of 20%. Pass in the batch size and epochs. And then I'm going to specify the callback function, which is tf.keros.callbacks.reduce learning rate on plateau. And what this will do is when it notices that the validation loss is no longer improving after a certain number of epochs, it will lower the learning rates to allow the model to converge more nicely. Alright, let's train it and start plotting the results. So I want to plot with matplotlib. So I'm going to create a new figure. I'll give a fig size of 12 by 6. And I'm going to do plt.plot. On the x-axis, I'm going to plot a range for each epoch. So epochs is what we had up here. If I take the range of epochs, it'll just give me my whole x-axis, 0 through epochs minus 1. And on the y-axis, I want to plot history.history sub loss. So I want, actually, why don't I plot accuracy? I want to plot the accuracy over time. So I want to do it for the training accuracy and for the validation accuracy as well. So this one and this one. And I can get that from history.history. Remember, history is where we stored model.fit. It has an attribute called history, which we can index on a metric to get the progression of the metric over each epoch. And I'll also give this a label. training accuracy. Okay, then I'll plot the same thing, but this will be validation accuracy. See val accuracy, and this is validation. Okay, then I'm just going to give this plot an x label, which will be epoch, and a y label, which will be accuracy. And then I'm going to enable the legend, which will allow these labels to show up for each plot. And then I will title it accuracy over time, plt.show. Alright, so you can see it's a bit of a rickety start. It may look like the model is performing better here, but in my tests it seems like it had to stabilize after a while before we could get a higher accuracy on the train set. So let's see how it does on the train set. Model.evaluate, x test, y test. Sorry, I meant test set, not train set. And you see we have an accuracy of about 67%. I think over a number of runs, the average accuracy is about 67 to 69%. So nothing really crazy, but also it's not very easy to tell. I mean, I wouldn't expect the model to perform really well in trying to predict whether a certain candidate has received mental treatment or not, mental health treatment, based on just a simple survey like this. There's probably a lot more that goes into a decision like that, and not necessarily our dataset is not necessarily capturing all that we need to be able to predict something like that with a high accuracy. But you can see it does decently well. It's nothing special. And I found that if we were to lower these neuron numbers, if we did like 64 and 64, we'd have even lower accuracy, something about 60%. So yeah, I mean, if any of you can find a better solution, please let me know in the comments. I'd love to hear about it. But that will conclude today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe, hit the bell, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.